In this video, we discuss quantization. We know that after we sample this continuous time signal, the signal becomes discrete in time. But if we look at the values of the sampled signal, these values can be anything in the real line. So the values of this sampled signal are still continuous. Digital communications cannot transmit continuous values. They have to discretize the value. That's the procedure of quantization. Quantization is a mapping. It maps the value of each sample into the nearest quantized level. A quantizer, the input is value, is any values, and then the output is a level. Next, let's look at an example. How do we design an 8-level quantizer? I'm using 8 levels for simplicity for illustration. Now, suppose suppose the value of these samples are in between -8 and 8. So therefore the highest is 8, the minimum is -8. Why do I use -8 and 8? For simplicity illustration purpose. So now I need to design a quantizer such that any values in between -8 to 8 will be mapped into 8 level. So this is the job of quantizer. Okay, I have the input x, those are values. The output, I call it x hat. So the input is from -8 to 8. I have 8 levels here in the y-axis. So this is a mapping. The input is value, the output will be level 8 levels. But the mapping we need to design, how we do the mapping. We're assuming that the value of the signal are in uniformly distributed in -8 to 8, which means that the value of these samples, so anywhere from -8 to 8, that's equally probable. Therefore, we're going to design a uniform quantizer. We're going to separate these values from -8 to 8 into 8 regions, uniformly divide them. -8, those are total range. I have 8 levels, so each interval, that will be 2. Each interval will be 2. So I have it here as 4, as 2, that's 6. And here, -4, -2, -6. Now you can see I divide this range, the minimum values and the maximum values, into 8 intervals uniformly. I have 8 regions from -8 to 8 divided up because it's a uniform quantizer. And from 0, let's say from 0 to 2, I'm going to design a level to represent any values in between this range from 0 to 2. We can design anything from 0 to 2, but just one level. So the best one, it will be 1 because 1 is in the middle. Anything here, anything in between 0 to 1, we have the minimum error because this is a middle point. So if we design here, this is 1. Any values in between 0 to 2, I will assign level of which has a value of 1. To be consistent with my notation here, I call it x5 hat. And this is our best assignment for the value from 0, because if we assign 0, when the value is 2, what's the error? The error is 2. Right? So in this case, the maximum error is 2. If we assign the value of this level as 2, then when the signal value is 0, then we have the error 2 as well. So there's the maximum error. But if we assign in the middle, maximum error only 1. So this is our best choice here. What about for the signal value from -1 to 0? We're going to assign the value into -1. Any values in between 0 -2, I assign it into -1. What about the value in 2 to 4? In this range, I'm going to assign it as 3. The value will be 3. So here 1, 2, 3. And then when this signal values in between 2 and 4, I'm going to use different color. I'm going to assign as, yeah, okay. When the signal values in between -4 to -2, I'm going to assign the value of -3. So there will be -3. So when the signal values in between -4 to 2, okay, or that's one level. The value of this level is -3. Okay. What about in this range, 4 to 6? I'm going to assign it to 5. Okay, so that's 5. Okay, you see this 5. And then on the same token, if I have anything in between 6 to 8, I'm going to assign it to 7. Okay, and then the same thing for this negative portion here. For values in between -6 to -4, I'm going to assign -5. Here will be -5. Here, -5. And from -8 to -6, I'm going to assign -7. So I call this quantization level. This is a quantization level x1 hat. This quantization level x2 hat. This quantization level x3 hat. And this is x4 hat. And this is x5 hat. This is x6 hat. And this is x7 hat. And this is x8 hat. And you can see this is a mapping. We have 8 quantization regions, 8 of them. And each region is mapped into one quantization level. We have 8 quantization levels, therefore the name of 8-level quantizer. This is the input and output relationship of a quantizer. Next, let's generalize the case. We're assuming that the range of the value of x is in -xm and xm. So xm is a value. In the example we just did, xm equals to 8. So this is a general case. This is xm. Suppose I still design an 8-level quantizer. So therefore, this range, it needs to be divided into 8 intervals. So each of them, I call it delta. I have 8 of them. Each interval is delta. So this is delta, 2 delta, 3 delta. And what is the last one? xm. And on the negative part, -delta, -2 delta, -3 delta, and -xm. So this is how I divide the values of the signal. And next, let's design the values for these levels. We have 8 levels we need to design. Okay, I have it here. If the value of the signal is in between 0 and delta, I assign to a level of half delta. Theta in this general case equals to 2 exm divided by 8. In this example, theta equals to 2. When the signal value in between 0 to theta, I assign it to half theta. When the signal value is in between theta and 2 theta, I assign theta plus half theta. So you can see here, if I have it here, that's theta, that's 2 theta. This middle point is theta plus half theta. Okay. And if the value of x in 2 and 3 theta, again, I'll assign them to the middle point, that's 2 theta plus half theta. If x in 3 theta to xm, I'll assign the level is 3 theta plus half. And then in the negative portion, in the negative value in x in minus theta to 0, I assign it to the middle point, minus half theta. When the value is in minus 2 theta to minus theta, still I assign to the middle point. You can see here, where I have it here, minus 2 theta, and this is minus theta. The middle point is minus theta minus half theta. Okay, the same thing for the rest of all those assignments here. Now we can see for this uniform quantizer, the quantization regions are all equal because we design a uniform quantizer. The distance between adjacent quantized levels, they are equal. For example, this quantization level, the distance is theta from x6 head to x7 head is theta as well. So therefore, this is a uniform quantizer. And uniform quantizer works well when the signal values are uniformly distributed. But if they are not, then this uniform quantizer is not optimal. Normally, for a lot of signals, there are higher probability for lower amplitude, for lower values. When the signal has a higher amplitude, they have a lower probability. For example, our voice signal, the magnitude are concentrating in the lower value. We can design non-uniform quantizer. When the values are small, we assign more values. And when the values are big, we assign fewer levels. So instead of uniformly assign these levels, we're going to design the distribution of these levels according to the probability of the values. Therefore, quantizer is a design module for digital communication systems.